thank you and welcome everyone. So this is Berta. I'm working as an application engineer at Ansys, and I will be showing today the capabilities of Zemax Optic Studio to perform stop analysis. This is the agenda that I have prepared for today. First, we will start with an overview of what Zemax Optic Studio can do. We will quickly review some applications for the aerospace and defense sector, and then we will see an example of a stop analysis, that is a structural, thermal, and optical performance of a lens system is basically a high power laser. We will see the optical development, how you can design the optomechanical structure, and then how you can analyze your system. Okay, so well, Zemax Optic Studio is like the gold standard software for optical design and simulation that delivers reliable results for a high precision optical system. So with Optic Studio, you can take an holistic design approach from the component to a system level. You can optimize the performance and make sure that your system can be manufactured. Industries that are using our software, aerospace and defense, consumer, data communication, healthcare, automotive, for a wide range of application, from endoscopes, satellites, telescopes to lasers. So when you open Optic Studio, you will find like an intuitive user interface that includes easy to learn tools and some wizards which enable efficient simulation and design of any optical system, from imaging optics to illumination system, including straight light analysis. Then you can analyze your system. The software includes the typical engineering tools to analyze the performance, such as aberrations, spot diagrams, wavefront error, and it also offers other more specific tools like full field aberration analysis to improve free-form designs, contrast analysis for MTF optimization, and image simulation to produce photorealistic images of your object scene. Then you can optimize your system to improve the performance of your design based on the requirements that you have, but also the constraints that are imposed. And this optimization will save time because you eliminate design iterations. There are, you can use, we'll see it later, you can use different criteria such as MTF, spot, or wavefront error. But, well, we know that meeting the requirements, the specification is not enough because each optical solution must be feasible and each optical design must be manufacturable. So with Optic Studio, you can perform a final tolerance analysis to ensure that your system can be manufactured. And for years, the Monte Carlo tolerance analysis in Optic Studio has been like the standard for simulating how designs perform in the real world. So you can be confident that your system will meet the real world performance demands of your customer. And finally, you can customize the software tailored to your needs. So with the API, you can create a standalone application, build your own analysis if it's not built by default within Optic Studio. And you can also control Optic Studio externally using C++, MATLAB, or Python. There is also a Zemax programming language, which is like a easy to learn programming language if you are not very familiar with this. And this allow you to write your own macros to automate repetitive processes. And you have also the option to build your own DLLs to create any surface, any object, source, or scattering function that are not shipped with Optic Studio. Okay. So Optic Studio has two different modes, is sequential and non-sequential mode. And we will see it in a bit. The sequential mode is intended for pure optical design because you can measure and optimize on aberrations, image quality, wavefront, diffraction, and so. So the main systems that you can design with this will be like lenses, microscope, telescopes, spectrometers, and so. And non-sequential mode is intended for illumination and stray light because you can measure and optimize the power that you have in your image, the bright, the uniformity, any noise that you have there, and so. So it's more for light pipes or wavelength sources, if you have cut objects, and so. And then there is also a tool that is called physical optics propagation. This is intended for design laser beam propagation because instead of tracing rays, the software propagate a wavefront. So this will be to take into account diffraction coming from apertures and so. Okay. And then just a few notes about how Optic Studio can be used for aerospace and defense applications. These are all like a complex workflow that involves more than one software, but just to give you an idea, you can design telescope, space-based telescope. So with Optic Studio, you will design the optical system itself, but then you can communicate with other software to include the housing and to analyze the final performance. Electro-optical infrared sensing, the same with Optic Studio. You will define your optical system and you can design it or tailor to the suitable waveband that you need, like visible, near infrared, and so. Obviously, you can design cameras and you can analyze the performance. And you can also improve and analyze the performance of your camera, taking into account the jitter effect, that is when the camera is under vibration, under a vibrating environment. And then another example that is quite common in aerospace and defense is LiDAR. So you can develop and validate your LiDAR system. But let's go to the real example today. So I will be presenting an example of a structural thermal-optical performance with the STAR module, which is an add-on for Optic Studio. First, stop analysis is a multidiscipline analysis consisting of structural, thermal, and optical performance analysis. So it basically estimates the thermal induced performance degradation of an optical system. And because you need to integrate different data from different software tools, the stop analysis can be challenging and quite time consuming. So the idea behind the STAR module will be streamline the integration between your mechanical tools like the AFEA tools and Optic Studio. So this will be like the ideal workflow that we propose with Ansys tools. So first you have your optical design in Optic Studio in sequential mode. You design it, you optimize it, and once you are happy with it, you can move it to non-sequential, you can export it, sorry, to your CAD platform, and then you can build your housing and re-import the full system, the optical design and the housing in non-sequential mode in Optic Studio. In this mode, you will have your source and you can trace rays and check the power that is hitting each optical lens and take this input to move it to your FEA software, like in this case is Ansys Mechanical or even Ansys Fluent, if you want also to perform some soft analysis, then you will run your FEA analysis or performance there. And with this data, you will import it via the star module within Optic Studio. So there you will be able to see how this thermal effect or structural effect affect the performance of your optical system. So first step will be the optical design in sequential mode of Optic Studio. I got this example here. Let me just open it. Okay, so this is a system quite commonly used in the industry. It has one scan mirror, and which is here. And these are just three focusing lenses. This is a window that is just a protective window that protect the image, which is here, and here is where the beams come to focus. So this will be source, mirror, going through the lenses, going through the window, and then we will have our image here. So this is it's a quite typical sequential system, and this is the user interface of Zemax Optic Studio in sequential mode. We have like three different spaces. This is the workspace when we have all the windows that we are using. This system explorer here is where we can define things that affect the full system. So here is where we control the aperture of the system, the fields that we are using, the wavelength, things like temperature, polarization, and so. And this ribbon here contains the tools that we are using first in the setup, like to analyze the two general settings of the system. In the analyze, we have here the image quality tools, spot diagrams, aberration, waveform, NTF, and so. In the optimize tab, we have the tools that we use to optimize the system. Same for tolerance tab. Here we have the different tools that we will use when we want to tolerance the system. The libraries contains info about the materials and the coatings that we can use. So here, Optic Studio came with different materials and different coatings provided by vendors. But if you need your own material or your own coating, you can also add it. Part Designer is out of the scope, but it's just like a easy CAD tool that you can use to build shapes that are not by default with Optic Studio. So to build a specific object and so in a CAD environment. Programming, as I said before, we have the possibility to control Optic Studio with this software here and to create our own analysis. The star tab is here and we will see it in a bit. And here in the help, This is, if you open it, you will find the Optic Studio manual. And finally, in learning and support, this is where you can access the forums, the knowledge base, and also the support if you need it. Okay. So going back here, this system is designed with this wavelength, and the effective focal length is 100 millimeters. The performance of the system is diffraction limited, and we can check this, for example, with the spot diagram. So if I open the spot diagram, we have the option to plot the iris here, and we can, is this shape here, we can see that all the rays go inside, so it will be diffraction limited. And once you have your optical design complete, and you are happy with it, the next stage will be to create the mechanical housing for the optics. This mechanical housing will give protection, and it's also like a sink to dissipate heat. So to prepare the mechanical component, you can convert the sequential system and export it to any CAD platform. So this will be done here. Here in File, you have this option here, and this will allow you to convert your system to STEP, STL, or other CAD files. So you will take it from here to your mechanical software. Okay. So now we are in this stage here. You convert your optical system to CAD, you go to your CAD platform, build the mountains and so, and you can re-import it to Optic Studio. And what we will do in this non-sequential mode of Optic Studio is trace the rays and see the flux that is absorbed in each of the components. Okay. So let me just show the file. Okay, so it's this one. So here we have like the same system before, but we have added this CAD component here, which is basically the surrounded of the here of the system. And this is a non-sequential mode of Optic Studio. The interface is the same, and the tools are different because they are meant for different analysis, but the structure is the same. The main difference between sequential and non-sequential mode is that in sequential, it means that we go from the object to the image in sequence. So we go object, surface 1, 2, 3, 4, 5, until the image. Here, instead of having surfaces, each row in the non-sequential component editor is an object. And the order of the object doesn't matter, because when you trace your rays, the rays can go, like in reality, wherever they want. So they can hit an object twice, they can skip an object, they can hit an object and be reflected back, but be transmitted at the same time, and so. And this is why Optic Studio non-sequential mode is aimed or meant for illumination system, because rays can be split, can be scattered, and can follow any random path. Okay, so yeah, this is the, for example, this is the lens here. This will be this one, and so. And the cut here. The cut part that we have import from our mechanical software has different properties based on the file that we have import. So we can define the material. Well, obviously we can position the file whenever we want, and we can tilt it as a regular object. But we can define specific materials, and with the dynamic link, we can connect Optic Studio with Creo and Autodesk Inventor to have all the parameters editable. Okay. Oops. Okay. And then once we have our system in non-sequential mode, we can get the flux, the absorbed flux that is in each lens. And for that, we will need to add a detector volume that enclose each element, enclose each lens. And I said before that the order in the non-sequential component editor of the object doesn't matter. This is true, but there is one exception, and is what we call the nesting rule. The nesting rule means that if two objects are placed in the same space, the properties of the intersection of the space that they share are defined by the object that is last in the non-sequential component editor. And this is important to take into account because it will allow you to define like holes in lenses, or in this case, to record the flux that is absorbed within a volume. Okay. This will be for the lenses, because we want to record the flux that is absorbed in the full lens. For other objects, most of the objects that we have in Optic Studio has an arbitrary shape, can be used as detector to record the irradiance data. For that, we can open the properties, and I can show you how to do it. Let's go back here. Okay, here. So we can expand these properties. Just close this. If we open the properties of each object, we will have this option here. And if we check this, it will mean that this object will be also a detector, and we can check the amount of power that is incident of it. Okay. This arrow here allows you to check the properties of each object. So for example, this standard lens, if I open here, there are different controls. You can control how this object will be drawn. And an important thing here is you can apply coating or scattering to any of the faces of the object. And this will be done expanding the properties and selected here the face and the coating that you want to apply. Okay, so we have our detector, and we have all the objects here. So when we want to trace rays, here we are using a source Gaussian. There are different sources that you can use in Optic Studio, but all of them has some parameters in common. the position parameters, and also the number of rays that you can trace to analyze and to draw. This is a different control. So I'm going to reduce just a bit. This is just to show how it will look like. And the power is also a common parameter. So when working in non-sequential, what we do is define the object in the non-sequential component editor and trace rays. So this is under analyze and ray trace. And here we have different controls. So we can use polarization, we can split rays, scatter rays, and this is just to ignore errors in case there is like a tricky ray that can stop the simulation. So the polarization here is important because it will, if you have it checked, it will take into account coatings and other properties, Fresnel reflection and other properties that you have in your object. If not, it will ignore any coating that you have applied. So I will leave it checked and we'll click clear and trace, and this will clear the detector first, and then we'll trace the number of rays that we have here. Okay, so well, this is quite low because I just trace very few rays for the sake of time, but the way that we have to check the results is in the detector. So here, if I open a detector window, okay, in the settings, I can choose the detector that I want to see. So in this case is the lens one. And I can also, depending on the type of detector, I will have different data to show. In this case, we want to check the incident flux or the absorbed flux. And we have also, this is a graph, but in each detector viewer, you have also the choice to see the data in form of text. Okay. And this is useful if you want to post-process this data. So you can take pixel by pixel the amount of power that you have there. Okay. And if I open the shaded model, so here we can also see the settings. Okay. So here we can also see the effect of this rays in the different component. So here we can see that some of the rays are hitting this cut part. The number of pixels that we see here is controlled in the non-sequential component editor with the draw resolution or with the number of pixels in the cut. Okay. So we have seen this. Okay. And this. And now this is the data that we want to export to mechanical or fluent or whatever. In this case, we are using a script because we don't want to do it manually. If you are interested, the script is a Python script and can be found here. And this script take the data from the detector. It checks the coordinate of the data because you need to use a single global coordinate system in the different software to make things easier. And what we do is in the programming tab, we use the interactive extension and run the script. Interactive extensions means that your Python or MATLAB or whatever script is making changes or working with the Optic Studio instance that you have open. Okay, so this will be the script. It calculates the local coordinate and it retrieves the absorbed flux value. And if needed, it converts from local coordinate into global coordinate. And the data that we have is a text file, which is basically the coordinates, so X, Y, Z, and the flux or the data that we are taking. And these files can be imported directly into mechanical, into Workbench, or into other software, into other mechanical software. So once you have this data, what you will do is running your FEA simulation in your software and export the results. So we will be in this in step 4 and 5, depending on if you are doing a mechanical simulation or if you are doing also the fluent one. And I have a video here that shows how to work in Workbench with mechanical. And so it's just 2 minutes, so we can see it. So the objective of this is to connect all the software. So basically apply a connection between the optics and the mechanical. And here what we can do in the mechanical is apply some structural loads into the optics. So the optics are under some pressure. And the lenses also will heat up in the environment due to the surrounding tube that we have. And all of this is taken into account. So here we have the same system, but in mechanical, and we are adding the housing, and then we will apply the thermal changes and also mechanical loads. So in this case, the connection between Optic Studio and mechanical can be done via a script, so it's automatic and you don't need to change anything manually. So these are the thermal loads. Okay. And once we have this done, mechanical will give a text file. And this text file will be the one that we re-import into Optic Studio via the Star module. So we will be, or Fluent if we have done. So we will be in the last stage of the workflow. First, a quick overview of what the Star module is. The Star module enables direct and an accurate simulation of FEA results from a structural, thermal, and fluent simulation. It uses a robust numeric fitting for accuracy, and it also has some visual tools which are easy to use to visualize the impact of these loads in your system. In this case, we are using mechanical because it's from Ansys, but STAR is platform agnostic. So you can load FEA data from any platform. And from there, you will have access to all Optic Studio analysis that helps you quantify and understand the impact of the optical performance of the system. And also to catch problem early in the design process. And to make it easier, automate import and analysis with STAR are possible to speed up the process and also to reduce manual errors and avoid the pain that is always in the communication between different softwares. Okay, so this is the Start tab. So at the beginning, we have some tools to load FAA data, to fit it, and then to assess the alignment, but also the fit. And then we can show the structural and thermal data summary. That is the thermal and structural data that we have for all the surface and volumes in our system. And finally, we have some tools to view and to analyze the performance. Okay, so I'm going to show you how to load this FAA dataset and how to assign them to our system. Most of the common surface types are supported with STAR, and these include free-form lenses and free-form surfaces. Okay, so if we go back to our sequential system, which is here, we will go to the Start tab, and here with the multiphasic data loader, okay, load. And I'm going to use this. These are the text files that are generated in mechanical or in your CAD software. So I can load them. Based on the format, Optic Studio will assign to deformation data or volumetric data. And here we can import structural data, deformation. We can import temperature, index of refraction, and also stress birefringence. So what we need to do is assign this data to any to the corresponding surface. So in this case is 4, 8, and we see here that we are applying the right data to the right surface. In this case, is very important to the communication between the optical and the mechanical engineer to make sure that we are using the same coordinate system. If for any reason we are not using the same, we can move it here. So we will be able to move this point data if we need it with these controls here. And we can change between global and local coordinates. This 9. Okay. And volumetric, this is surface 8. And this is temperature. Okay, and we can see here like the temperature is across the whole volume. Okay. So once we have everything, we click OK. And this data will be imported in our optical system. Okay, and here we can see the change in all the analysis tools that we have in Optic Studio. So in this case, we have the wavefront here and the spot diagram that has changed when we add this thermal or this structural deformation. Okay, so here we have summary of the data that we have loaded. And this is important because here we can check and uncheck this data to take it or to not take it into account in the performance. So if I check and uncheck this, we will see a change, and this will allow you to analyze and to determine the data set that has the biggest or the lowest impact in the performance. And this is the same for the volumetric data, in this case for temperature. So basically we can see the performance of the system taking into account or not taking into account this data. Okay. So this is the multiphysics data viewer. This is a tool that you can use to review the data set without assigning to an optical surface in the system. So this is basically to verify that you are using the correct file and the file is fine and it doesn't have any error before assigning to your optical surface and before performing a numeric fit. There is also a symmetry tool, and this is add to load symmetric data like axis symmetric or planar symmetric. So using this tool, the data from half or from quart model can be loaded onto the system, and you don't need to record the full geometry of the lens. So basically it's quicker. Okay. So you will be able to load multiple partial data onto the lens file at once and save it as new. We see here, this is how to load FEA data and how to assign each data set to the surface with the drop-down menu. Same for thermal, and yeah, as I said before, take into account the global and local coordinate system. If needed, you can move or change this system with this menu here. Then we have a tool that is the data fit assessment, and this is to control and to adjust the numerical fit settings for each data set. So in the graphic, you can see the difference of the data set and the numeric fit. And also you have a numerical, this is the visual representation, but you have also some numerical data like the RMS fit error and peak to valley. And also you have some settings if you need to shape and control the fit refinement. You can also check the alignment to see the entire optical system with the data set, and this will give you an overall view of the alignment of the data in your system. We saw this structural and thermal summary is to show an overview of the surface that we have in the system and that have a structural or thermal data set assigned, and you can enable or disable the effect of this data set. And the system viewer, it displays a system-wide view of the deformation and also of the change in the optical properties. So in this case, we can see a change in the index. In the settings, you can control the information that is displayed. So you can display the deformation, temperature, change in index, or directly the raw value of index. And then there is also a performance analysis, and this is a tool that allows you to see how is contributing to the overall change in the optical performance of the system. So with this tool, you will see which surface is contributing the most or the less to the overall performance change. And there is also a performance of on a system level basis. So you can check the nominal, the structural, the thermal, and all stop data. Deformation plots to show the directionality and the magnitude of the deformation on a surface. And thermal index plot. This is to display the index against the temperature for each surface that has a data set assigned to it. So you can see how the index is going to change or is changing with the temperature for each surface. Another important feature is the surface sag analysis. These are by default within Optic Studio, but the difference is that you can see the difference in the sag with this data set or without this. So in this case, the sag of a lens will be the one, this one, like, for the original system. When we add this data set of deformation, we have a different one. And if we remove it, the sag of the lens will be different because we are like deformating or changing the shape of the lens. And the same, we can see the difference in the wavefront. And the recap of this module will be like the STAR module take advantage of all Optic Studio tools. So basically you need to load your FEA data and use the Optic Studio tools to analyze and to see the effect. So in this case, we are using the wavefront, spot, and image simulation. Okay. And well, we have seen that to analyze the thermally induced structural deformation, we have loaded something around 14 data set, and we have assigned to the lens surface in the system for each thermal condition. So if you want, let's say that we want to analyze like 7 temperature points, we are going to have nearly 100 data set. So this data loading will be pretty time consuming and prone to error. So what we do is with the API, we use it to facilitate this process and to avoid mistake. There is a STAR user extension. It's available to load multiple data onto the lens system. And the user extension applies the data set that you have from all the time and temperature points in an automatic way. So you don't need to do it once by one. And in the background, a copy of the lens system is created and saved with a number. So basically, this extension here is available in the user extension. You need to download first from this article. Will allow you to load multiple data set and to assign in an automatic way to your system. And once these data set are assigned with the star user extension, the star user analysis can be used to load and display the analysis results for all the system. And this provides a more efficient workflow when dealing with multiple groups of data set from different time and temperature point. So you can check the fit results for all surfaces in all time and temperature points. And also analyze the optical performance degradation, comparing the results of different temperature in the same analysis window. Okay, so this is here. We do it one by one, and here we can plot with the extension all surface at one and all surfaces at all time points. And yeah, this will be an example of how to use the star user analysis to run different analyses for all temperature points and evaluate the performance, the optical performance degradation. So in the first graph, we can see the spot size change with changing system temperature in a single analysis window. So we can see how this stop is changing with the different temperatures that we have. And also things like the contrast of the lens system at different thermal condition can be shown or monitored through the MTF analysis. And again, study how the NTF is going to change with the temperature in different fields and in different focus. And yeah, this is everything that I got for today. Thank you for the opportunity and for your time.